Okay, welcome everybody to this series of webinars hosted by CTS, Ferroperm Piezoceramics. My name is Erling Ringgaard, and on the screen I hope you see a list of webinars. We have 6 webinars planned for this autumn, and the first being today and the last one in the middle of December. So I hope that that you are seeing my screen and that everything's working. I think that the chat is disabled, but if you have any problems hearing or seeing, you can just put a question in the Q&A, then I can see it. Okay, we're ready to start. So as I mentioned, this is the first webinar, and you see the list of talks further below. I'll also have the second one, and number 3 and 4 are by external guest lecturers, Thomas Kelly and Thomas Savara, and then we will end with 2 from my colleague Rasmus Lormøller. So let us just begin now. Just a minute. Good. So the title of the talk today is Piezoelectric ceramics and their properties, and this is meant as an introduction to these materials. Then we'll go into details with more specialized subjects later. But this is an introduction to the very special properties of these materials, and I'm sorry if we have to go a little fast, but you can. We hope that there'll be some time for questions later on if something is unclear. So the outline of the talk is like this. I'll start with an introduction with a short recap of the phenomenon of piezoelectricity and a little bit about crystal structures, and I'll introduce the piezoelectric coefficients. Then the next part is about the materials that we make, piezoelectric ceramics, and with a lot of focus on PZT, which is still the most important piezoceramic commercially. Then in the third part of the talk, I'll give some hints, maybe more relevant for customers who are maybe designing their own piezoceramic parts. And I'll tell you a bit about what can go wrong and some possible means of avoiding problems. Yes, let's get started. So to begin with, the definition of piezoelectricity is like this: formation of electric polarization in certain materials when you subject them to a mechanical stress, or vice versa. If you subject them to an electric voltage, that you get a formation of mechanical stress. And this is an effect discovered and described by the Curie brothers back in 1880. So I normally use this sketch to show what's going on. You should imagine a piece of piezoelectric material. I'll just get a laser pointer here. So the material looks like this in the equilibrium state. You should imagine a non-conducting piezoelectric material with conducting electrodes on the top and on the bottom. And this is a piezoelectric material, and in this case we even have a polarization vector which is going in the direction from one electrode to another. And the reason for this polarization vector is the dipoles inside. You have a number of aligned dipoles, meaning a minus and a plus, a negative ion and a positive ion that are connected, and the direction of the dipole is the same as the direction of the polarization vector. That was the starting point in equilibrium. Then if you apply a mechanical stress, like in this figure, you affect the whole system, and you shorten the dipoles, and the response of the system is that voltage, an electric voltage is generated, like you see here. In the other case here, in figure C, instead of a voltmeter, you put a wire, so the two terminals, the two electrodes are shorted. So in this case, when you apply the stress, actually electrons will flow through the wire. And finally, in the figure D, we see the opposite, or the converse effect, which is when you apply an electric voltage, like from this voltage source. Then the additional charges, you see extra plus charges and extra negative charges here. These charges will actually affect the ions inside the material, and extend the length of the dipoles here, meaning that the whole material will become longer in this direction, and at the same time it actually becomes shorter in the transversal directions. I have a couple of examples. So first, a very simple example of how you can use the direct effect. This is this barbecue lighter, where you want to ignite the stream of gas, and you do that by a spark generated by the piezoelectric material. So when you press the button, some stress will be applied to piezoelectric ceramic part or component inside, and then you actually, through this current going through the wire, you actually generate a spark that can ignite the gas. An example of the converse effect, also very simple and cheap component. So this is a piezoelectric loudspeaker, which can play a melody when you open this gift card. And the background is that when you apply a voltage, as I said, you get a mechanical response. So if the voltage is actually an AC voltage, then you get a sound signal from the component with the same frequency as the voltage signal. And in that way, you can actually play a little tune. There's yet another example here, much more advanced, where you actually use the piezoelectric effect in two ways. You use first the converse and then the direct effect. And in this case, the application is baby scanning, generally medical imaging by ultrasound. So the ultrasonic signal is generated by, again, an AC voltage, but now it's a much higher frequency. It could be 2 megahertz. So it's ultrasound. And then the sound is transmitted through the human body in this case. And in case of a pregnant woman, you see that the sound signals are going through the skin and maybe a layer of fat, and then the uterus, and you see different types of tissues here, and get a very nice resolution of the image. When you pass the sound signals through the tissue, there'll be some echoes traveling back, and these echoes are received again by the piezoelectric ceramic, because it's able, through the direct effect, to convert the pressure signals to electrical signals that can be processed in the ultrasonic scanner. So sound generation through this effect, through the direct effect, and then detection of sound echoes through the other effect. And by keeping track of the time differences, you can see the difference between something very close to the sound emitter up here and something far away, because of the time of flight will be different. And also you can detect the angle difference also from a time difference, because the scan may go from this angle and then through to this angle and then back again. So two very simple examples and one quite advanced. So before I go on, I will just show two small demo videos. I hope it will work more or less. So I'll go out of the presentation here and try to share the screen with the two videos. So I think I'll start the video from start. So what I've used here is actually the little piezoelectric loudspeaker that I showed you before in the second example. I'd like to show that if you hit it, if you apply some mechanical stress, there will be an electrical signal. And this I do by just connecting a very cheap oscilloscope to this piezoelectric component, and then you'll see a voltage signal on the oscilloscope. So let's see if it works. Just a minute. I think I need to share another one as far as I can see. Sorry about that. Okay, I think it may work now. Sorry. So again, I repeat, you see this little loudspeaker with two wires connected, and I want to show a voltage signal when it's hit by a little object. So let's start and see. Here you see this little oscilloscope connected to the PC, and this is the screen with the voltage signal. Okay, so now you see something rolling down, and you saw a voltage signal on the oscilloscope screen, and now a larger object, and that was it. So if you noticed with the larger component hitting it, the voltage signal was stronger as it was supposed to. So I have another video showing the converse effect. So I'll stop sharing this one and try to find the other one. So just let me share it in a moment. Okay, so in this case, I use the same small oscilloscope. It also has a signal generator built in. So I'll just apply some AC signals, and then you can hear the sound coming from the loudspeaker. So let's start. On the screen, you see the settings. So 1 kilohertz. And now I start the sound. I think you hear a weak signal. Turn out the amplitude and change the frequency. I can also change the shape of the signal. So now it's a square wave or almost square. It's not a very good generator. Okay. So that was the end of the two demos. I hope you could see something. Otherwise, it was a long break. So I'll stop sharing this and go back to the presentation. All right. Okay, so let's go on now. After this little demo, I'll tell about the background of what we saw. So piezoelectricity is related to symmetry. So if there is a symmetric structure, there will be no piezoelectricity. So in short, symmetry is described by in crystallography by different point groups. So as I said, it has to be non-symmetric or asymmetric, so we can actually disregard the central symmetric point groups, and then there are 21 structures left, and then one more has to be disregarded because of some symmetry elements. Then there are 20 piezoelectric point groups, and they can be divided into 10 pyroelectric ones and 10 that are polar neutral. The polar neutral ones, one example is quartz. So quartz can be in these two different symmetries, a hexagonal and a trigonal one. You can also look at the material PCT, which is generally in these two forms. And if it's above the Curie point, it has this central symmetric form, so it's not piezoelectric in this form. And there are also other cases of piezoelectric ceramics with other symmetries. And finally, the structure of a pole piezoelectric ceramic will be this general structure, or it will be equivalent to this one. And then ferroelectricity is actually a phenomenon seen in a subgroup of these materials. So I'll not have time to explain all this now, but you see piezoelectric materials with the definitions of the effects, and the point that these materials have to be non-central symmetric. And I mentioned that ferroelectric materials is a subgroup of these pyroelectric materials, and in this case you can actually switch the polarization by using an external field. So I will move on and show an example of this switching. So you should imagine a piezoelectric ceramic material as a material with random orientation of the grains, and therefore you have no net piezoelectricity. You can see all these dipole arrows are pointing in random directions. Then when a field is applied, you can look at this graph and see that the polarization and the dielectric displacement are increasing as you increase the field. And in the microstructure, this is seen as alignment of these arrows of the dipoles, or domains, I would say. And then at a high field, all the domains are fully aligned in principle. When you then decrease the field again, you'll get to this state at zero field, where you have most of the domains, these little volumes of same dipole orientation. You have most of the domains that are aligned in the same direction. And then you can go to a negative field, and you will actually see the opposite effects compared to what you saw on the right-hand side. And then you'll just, if you cycle the material through an AC field, you'll basically follow this external hysteresis loop. And in the process of piezoelectric ceramics, this is actually what we want to do. We want to get to this polarized state. Okay, now some details about how you quantify piezoelectricity, how you can actually distinguish between good and bad piezoelectric materials, and see which materials are used for this or that application. So I've written some equations here. They probably need a bit of explanation. The first one here is actually showing the direct effect. So this Greek letter sigma is showing the stress in a certain direction, and the direction is indicated by the letter P. I should maybe explain what the numbers mean. So P can be 1 to 6, and actually it shows in which direction the mechanical signal is applied. So in the case of P equals 3, it's actually applied vertically. So if you look at this figure, it's applied like this arrow with the force from above. And I should also mention that this polarization vector is by definition always parallel to the 3-axis. And then the 1 and 2 axes are just perpendicular to the 3-axis, like this 1 and 2. Then back to the equation. If you want to find the electric field E in this direction, again, let's look at the 3 direction, like indicated here. You have an electrode on top and on the bottom. Then, as I said, this is also the 3 direction. So in that case, I, the electrical index, will also be 3. So what you see here is an application of a force in the 3 direction, and then a measurement of an electric signal through this wire, with this terminal, also in the 3 direction. So the E3 will be found by taking the sigma 3 and multiplying by this G coefficient, and it should be G33 since both I and P are 3. And then you need to find this coefficient which describes the material, and this can be found in a table of values from the supplier of the material. So that was about G33, and you can also look at the converse effect over here. And if we again look at the electric field and again look in the 3 direction, we can just again let I and P be equal to 3, and then you'll find the strain, as you see here, the relative displacement by multiplying another coefficient, now the G33, by the electric field in that 3 direction, and then you can find the strain. There's a relationship between these 2 coefficients that I mentioned, the G and the D coefficient, and in the case of G33 and D33, it's simply the relative permittivity in that direction that is used to convert from D to G. Yeah, final point here is that if you are working at resonance, you can find the ratio of input energy to output energy as the square of a coupling coefficient. So this is another way of expressing piezoelectric activity by a coupling coefficient, and this is relevant at resonance. So of course you need to again have the right values of I and P so that you have a resonance that is relevant for your exact case. And in this case of a plate with electrodes in this direction, and looking at the vibration in this direction, it will again be K33. But you could imagine other values of I and P if you apply the stress in a different direction, or if you measure the voltage in a different direction. Okay, I will move on now and just take some examples here. So here you have just a little cube of piezoelectric ceramic material. It's one of our materials, and it's just in order to illustrate the numbers and the orders of magnitude involved. So here you see the stress in the case where you apply a force of 10 Newton. So the stress is found quite simply by just dividing by the area. And then you use one of the equations I showed before, multiply by G33, that you look up in the table for Piezo27, and then you find this electric field, and this can be converted to a voltage of 27 volts by multiplying the field by the thickness. So quite a high voltage for a rather small force of only 10 Newton. On the other hand, if you look at the converse effect, you need to apply a very high voltage to see a clear effect. So with 1000 volts here, and using the equations from before, you actually get to a pretty small displacement of only 425 nanometers, or 0.4 thousandths of a millimeter. So quite a small displacement. On the other hand, you should notice that it has a very high blocking stress, meaning that it's a quite mechanically strong effect. You can actually move something by this distance, even if it's quite heavy. You can have this stress of 1.8 megapascals, or equivalent to this force of 183 newtons. So almost 19 kilograms you can lift by just using this small cube of ceramic, if you have a high voltage of 1000 volts. Okay, so the next three slides are maybe a little beyond what you'd use for normal applications of piezoelectrics. So I just want to put some of the effects into a larger picture, but I'm sorry if it's going a little more into details than some of you would like to. So I put here basically some equations that describe the mechanical and electrical conditions for materials. Let's say some insulating material, solid material. So to begin with, if you want to find the strain as a function of the stress, the strain S and the stress sigma, you use something which is pretty similar to Hooke's law. You know that if it's an isotropic material, you just need Young's modulus, and if you have different directions, maybe one parameter more, like Poisson's ratio, then you can actually describe the behavior of an isotropic material. And similarly, the electrical behavior of this insulator is described by the electric field, and then just one number, the permittivity, then you can find the dielectric displacement from this. So what I want to show now is that for these materials that we are talking about, it becomes a little more complicated. To begin with, if it's an anisotropic material, the equations look the same, but instead of 2 coefficients in this S tensor, it can be, in our case, 5 coefficients, and for a complicated crystal, it could be even, I think, up to 21 coefficients. But in our case, we need 5 coefficients instead of 2 in the isotropic case. And then for the electrical case, it's not enough with just one number describing the permittivity. You actually need, in our case, 2 numbers, but it could be up to 3 different numbers describing the permittivity or the dielectric constant. Okay, but now that we agree that it's a piezoelectric material, we actually need to add something else, because in the mechanical case, you can actually see that in addition to this, let's say, purely mechanical part, there'll be a piezoelectric part, because if you have a certain electric field, you need to multiply that by the D tensor, and then you get the full strain. So this full strain will be a sum of the elastic and the piezoelectric contribution. Similarly, for the electrical case, you have something which is purely dielectric, and then this piezoelectric contribution, which is a function of the stress that you apply. But again, you see that the D coefficient is appearing in both equations. Okay, and this can be combined if you like to. So this is just a collection of tensors that are arranged as matrices, and then you can actually get the full response as a combination of strain and dielectric displacement, and that will be a function of the stress sigma and the electric field E. And the reason that these are underlined symbols is that it's several elements of a matrix that are hidden between these symbols. And what you need to know then is the material properties, and if you arrange them like this, you actually have a big matrix that you can multiply with this matrix. I'll skip these extra points. You can also express the piezoelectricity using other tensors than the first I showed. So this is how it may look. As I said, you have the material properties in this big matrix, and you see this is mechanical part with this S tensor, which is called the compliance tensor, and the piezoelectric part is in the red squares, or in the red rectangles. That's the D coefficients, and finally you have the purely dielectric behavior shown here with the epsilon values, the relative permittivities. Okay. So finally, I should also mention that all that I showed here is for the ideal case where you just have normal real numbers here, but I will cut this short and say that generally there will be some losses of some type, and if in case of a dielectric material, typically it will not be, or generally it will not be an ideal or perfect dielectric material. So you actually need to introduce some kind of loss, which is usually related to some resistance or conductivity, you may also call it. And in that case, you actually use what we call the dielectric loss tangent, tan delta, to express the magnitude of these losses. Also, I can mention that in the mechanical cases, there's also mechanical losses, very often described by the mechanical quality factor. And like before, you can actually also express this as a loss tangent if you, as input, use some mechanical coefficients here as the compliance tensor. So for a specific direction, you can take the imaginary and the real part of the compliance coefficient, and then you find the mechanical loss tangent by that. And finally, you can do the same for piezoelectric losses, where you'd use a piezoelectric coefficient expressed as a complex number in order to find the loss tangent. Or otherwise, you could also use a piezoelectric quality factor, which is the reciprocal of the loss tangent. And that is similar to the other cases. You may also choose to use quality factors, which are reciprocals of the loss tangents. Okay. Now a word about resonance. I can describe a resonance as a standing wave in a material, and you can actually relate this to the case where you play a sound inside a tube of just an open tube with air, and in that case you'll see that there will be a magnification of the sound, or amplification of the sound in case of a certain wavelengths, and the lowest frequency or the longest wavelength is when you have a 1/2 wavelength, like shown here, which is equal to the length of the tube. But there's also other resonances where you have 2/2 wavelengths or 3/2 wavelengths. So here you see the two different wavelengths, you know, what I call λ3 and λ1. And such resonances you will also see in a piezoelectric material if you just apply let's say, a sweep of frequencies, you'll see a piezoelectric resonance for these two different wavelengths or equivalent frequencies. Yes, I think I'll move on. And I think I'll also skip the equivalent circuit for now, because I'd like to show you that you can have many different shapes of piezoelectric materials. And these are some of the most important ones. So one case is just a circular disc. And in this one, you will have a very characteristic resonance where you have extension in the radial direction. And this is described by a coupling coefficient Kp, the planar coupling coefficient. For that same thin disk, you will also see a resonance which is described by Kt, and now you have the extension in the thickness direction. I can also mention that if you have, for example, components like we make, it could be a ring like here or a tube. You'll also have some specific resonances for these components. In principle, 3 different types of resonances for each of these two. And finally, something I didn't really show yet, but there's also something called a shear mode, where you have this shear displacement shown by the arrows. And it should be noticed that now the electrodes are not in the same direction as the poling axis. Actually, the material was poled using electrodes here and here, and then you remove those electrodes and actually apply new electrodes in order to exploit this shear mode. There are other resonances as well, as you see here, but we will not go into the details with those now. This is what some of you already have seen, I'm sure. It's a piezoelectric resonance seen at a very specific measurement called the impedance spectrum. So if you plot the frequency on the x-axis and plot the electric impedance on the y-axis, actually the numerical or absolute impedance, then a resonance that I talked about before will be very characteristic. You will see a minimum like this, and then a maximum. And on the logarithmic scale here, you'll see it even clearer, a very distinct minimum here and a distinct maximum. And these two we'll call the resonance frequencies. So this is called the series resonance, and this is called the parallel resonance. But these two frequencies together really describe the resonance as I talked about. And the resonances and the frequencies are dependent on the dimensions. If you think back to the length of the tube, as I showed before, that has influence on the wavelength, then you may understand that the frequency really depends on the dimensions of the part. So what you see here is an impedance spectrum of a piezoelectric circular disc, 25 millimeter in diameter, and then the 25 millimeter and the sound velocity of that material will actually yield a resonance frequency here of 80 kilohertz. That disc is also 1 millimeter thick, so that thickness will give another resonance, a thickness resonance, which is here close to 2 megahertz. So you see 2 distinct resonances here, and then also some other smaller ones, and these are the harmonics, the overtones, and I mentioned the lambda 1 and lambda 3. So this one is actually equivalent to lambda 3, basically 3 half wavelengths inside the solid part over the diameter of the part, you could say. And this is then lambda 5, 7, 9, 11, and so on. Okay, there are a lot of different types of materials that are piezoelectric. I'll just mention that what we are normally working with in our company is the piezoelectric ceramics, so mostly PCT, and also some other materials that are used at higher temperatures. We call them either Aurelius phases or BLSF, short for bismuth layer structured ferroelectrics. I've listed a lot of different properties here that will show the difference between the different categories, but in order to save time, I'll not go into details with those numbers, but just by looking over them, you can see some large differences between the magnitudes of these different coefficients. I should also mention, since we are now a part of CTS, that CTS materials are generally also coming from the PCT category, and then also some single crystals like these that I call modern single crystals with extremely high coefficients like here. Okay, so some words about the nature of the dipoles. I mentioned that we have some absence of symmetry, so some lack of central symmetry, and this is really due to the arrangement of the ions inside the unit cell. So from a crystallographic point of view, a unit cell of a typical ferroelectric material could look like this. So this is barium titanate, and you see you have barium and titanium and oxygen marked by these colors. And when you have this ferroelectric state where you can see piezoelectricity, you will actually have a small displacement relative to this center plane. So the titanium is not exactly in the middle between the top and bottom plane. It's actually displaced a little bit above, and then here you have the oxygen and ions displaced a little bit below. And this lack of symmetry, or this asymmetry, is actually the background of the dipole that will give you the piezoelectric properties. I can also show you how the unit cell is actually distorted. You can compare it to this symmetric state where you are above the Curie point. In this case, there's no piezoelectricity, but if you go below that temperature, you see the displacement, the tetragonal displacement in this case, and this is what gives you the ferroelectricity and the piezoelectricity. Okay, so some words about PCT that I have mentioned already. So PCT is what you could call an abbreviation of a chemical formula. So you see there's lead and zirconium and titanium, and then some oxygen. So in short, called PCT. And this actually means that compared to the case before, you will not only have titanium in the center of that unit cell. You will have either zirconium or titanium. So the X describes the fraction of titanium, and the rest will then be zirconium. And this can be showed in a phase diagram where you can see how close you are to only zirconium, or how close you are to only titanium on that so-called B side. So it turns out for PCT that you get very good properties if you are very close to 50%. If you are close to a phase boundary here called the morphotropic phase boundary, you will have a maximum of properties, and this is why people prefer to use, for example, PCT with close to 50% instead of pure lead titanate, which is also a ferroelectric and piezoelectric material. And on the other side here, you actually have a different kind of distortion called rhombohedral distortion. This is also a ferroelectric phase. And I showed you before that you can have an asymmetrical structure, and this is again that one. And this one is stable when you get above this line. So depending on the composition, it may be above 490 degrees or for PCT close to 350 degrees. if you get above this temperature, you lose the polarization because you get to this state, and when you cool it down again, everything will be randomized so that you will not have a piezoelectric material unless you are able to align the dipoles like they were before, coming from the manufacturer. Okay, so I think I'll skip explanation of the high temperature materials because this structure is a bit more complicated. I'll just mention here that you can tune the properties of the materials by adding some dopants. You can add small amounts of some cations like lanthanum or thorium or other more or less exotic dopants. And either you get properties like what we call soft doping, or by doping with these elements, you can get hard properties as showed here. There are also other ways of changing the composition, but the most important ones are soft doping and hard doping. And you see the effect here that for soft doping, you generally raise some coefficients and some properties, and some others are decreased. And for hard doping, it's very simple. The sign is reversed. So, for example, permittivity that went up for soft doping will go down for hard doping. Okay, I'll move on now, and just show you an overview of all the different materials, and you have the explanation for the large number of materials. If you consider the slide before that you may want different combinations of let's say soft or hard properties, and you may need something which is normally soft, or it could also be something which is very soft with for example, a very high permittivity. So there's a number of different materials in our catalog, and if you look at the CTS website, you'll find even more different materials, and you'll hopefully be able to find exactly the material that matches your application. I may also mention that in addition to PCT, which are, for example, these four categories here, I showed that we have the high temperature materials, but I should also mention that we have some special materials that are characterized by low acoustic impedance, and we obtained that by adding porosity. So we intentionally make them porous, and that actually gives a lower density and also lower acoustic velocity, which means that these materials are more broadband, and they can more easily transmit sound into a material or a medium like water, which has a much lower acoustic impedance than for example, a ceramic material. Okay, this is an example of a table of properties. So just to mention that some of the properties that I mentioned before for soft and hard materials, you'll actually be able to verify when you have time that the materials are characteristically different if you compare, for example, hard and soft PCT. Some micrographs showing the structure, the microstructure of such piezoceramic materials. This is in an electron microscope, and this scale bar is 5 micrometer in each case. You see some difference in the microstructure between some of the soft and some of the hard materials here. And this lead titanate one is very fine grained, as you see. And here you see a very different grain morphology for the high temperature materials. The bismuth titanates, these are like platelets. And finally, what I told you before, the porous PCT material, where you can easily see some porosity that has been added deliberately. This is an example of some of the shapes we have. A lot of different shapes are available upon request. A quick overview of the manufacturing process. So I have shown here in red basically the processes that are related to powder. So first you weigh out the raw materials in the right ratio, and you mix them carefully, make them react together at a high temperature. Then you can reduce the particle size by milling. And finally, you add a binder, for example, using a spray dryer, where you can get the individual grains to stick together in larger granules. Since you have added a binder covering the surface, you have a material which is very easy to press. So when we start an order, we start by pressing the material uniaxially, and then we have a specific shape, which is not too far from the final shape. Next, we can remove the binder by debinding, and then a high temperature heat treatment called sintering, where you eliminate the porosity. And then you actually have the ceramic part, which is quite robust and strong. You can do some further machining, like plain grinding or lapping, and you can do round grinding and lens grinding and cutting in order to get exactly the right shape you need. Then you apply an electrode, for example, by screen printing, and then you can finally do the poling. And here you should think back to the hysteresis loop I showed before, where you see the alignment of the domains when you apply the electric field, so that when you remove the electric field, most of the domains will still be aligned, as I showed. And now this ferroelectric ceramic has been turned into a piezoelectric component, now that you have aligned the domains, so you have a net polarization. And finally, you inspect the components, and then you can actually sell them to a customer. Okay, I think I'll skip the part about multi-layer components for now. We will not have time for this. So I'll move on. These are some typical dimensions. I would say it's only typical dimensions. We can actually make larger parts, for example, than this. We could, in principle, go up to at least 140 by 140 millimeters for special orders. But it's always important to discuss extreme dimensions with the supplier before you start ordering. I can also refer to our list of frequently asked questions that you can find on our website. Some of the questions you may have, even after this introduction, may be answered by some of these points here in our FAQ section. Okay, I have a little time for showing some things that may go wrong when customers order piezoelectric ceramics. So one possible problem could be that something which is important is not specified. So this is what I call under specification. You could also imagine the opposite, that something is specified on the drawing, but actually not really important. One example could be that some designers may be used to specifying a roughness which could be very low and easy to obtain with a metal, but maybe for ceramic it will be very difficult or expensive to obtain such a low roughness. So it's actually relevant to think about which tolerances are put, whether they are important or not. Another point could be conflicting specifications, because the geometry of a material may actually be in contradiction with to some other properties that are really related to the physics. So, for example, specifying specific dimensions may not be compatible to a specific capacitance, because the capacitance is really governed by the dimensions and the dielectric constant, or also called relative permittivity of the material. And we have what we call the piezo calculator that can help you actually see what comes out of a specific material choice in a specific geometry. Finally, you could also imagine that you want to choose a certain shape, and then this shape does not fit with the resonance that you would like to obtain. And I have an example of that in the end. So this is how this piezoelectric calculator may look. So if you input a material choice and some geometry by shape and dimensions, then it will try to tell you the capacitance and also the resonance frequencies if the normal simple equations are followed. In some cases, these resonances will not be correct if you have a geometry which is far from the ideal, and you'll see that in a moment. I have a case here where it will not give the correct answer. So, for example, if you have dimensions that are very close together, you may have a coupling between different vibration modes. So I have a little example showing how you can use finite element modeling. And so the case here is a Piezo26 hard PCT material, a disc with a diameter of 20 millimeter. The customer would like to have a very precise resonance frequency in the thickness mode of 200 kilohertz. So if you use a simple calculator, you probably expect you should make it at a thickness of 9.55 millimeter. Actually, this is the result, and you wanted to have a resonance frequency exactly here, but instead you basically have 3 resonance frequencies that are in competition, and none of them are 200 kilohertz as you wanted. So then we went to a finite element modeling to see what was going on, and you could actually even foresee these complicated resonances by doing the finite element modeling. You see they are not completely predicted, completely precisely predicted, but you see exactly the same trend with the FEM model. And then with a different height in simulation, you see that you can actually see the influence of the thickness. So I'll have to go a little quickly now, but I'll just mention that that we have looked more carefully at these 4 different resonances for the green case here of a 9.3 millimeter thickness. So the FEM model will actually tell you how the displacement is. This is how the radial planar coupling mode will look in terms of actual displacement. Of course, it's very much exaggerated so that you can see what's going on. But then looking at what should be a thickness resonance, you can see that actually it's much more complicated than a simple thickness resonance. You would have liked to have probably only red color here, and the red should be more or less blue. And instead you have actually this complicated displacement all over the component. And for the next mode, number 3, it's even more complicated. You have a very unpredictable pattern of displacement. And finally, for the highest frequency at 230 kilohertz, again, something which is not what you expected. It's not just a pure expansion contraction as you hope for. And the reason for this is actually that the difference between this diameter of 20 millimeter and the height of 9 millimeter is too small. They are so close together that you will get couple modes, for example, looking like this or like this. Okay, I think 1 hour has passed, so I should move towards the end. I have just a list of relevant literature here. Some interesting books where you may find more information, and there are also 2 standards telling more about how to measure the piezoelectric properties. And to conclude, I told you about Piezo-T looking like this in the general formula, the most important piezoelectric material for commercial applications. I also showed how you can tailor the modern materials either by changing compositions and generally doping them. And you can also introduce porosity to tailor the properties even further. And we saw that often there's a trade-off between properties that are in conflict. So you may look in our material table and find the material that suits you best. I talked about uniaxial pressing, the most common shaping method for the industry, I would say. But if you want to have thin layers used for multi-layer components, you can also use tape casting. I didn't have time to show that in detail. Then I talked about resonance and resonant operation, where the geometry of parts is really important, and you, from the properties like frequency constants, you can actually find the desired geometry of those parts. But for more complicated cases, you should look to advanced methods like FEM modeling to try to predict the behavior. Okay, that was my final slide. I will stop sharing for now, and I will have a look in the Q&A. I think if anybody has questions for this talk, where we covered quite a lot of material in a short time, if there are any questions, you may put them in the Q&A, and then I'll do my best to answer. And in case you are not ready with your questions yet, but some questions will come up later, you of course very welcome to contact us by email and ask about specific materials or specific applications. Okay, I see now in the Q&A that we have a question from Olivier. What is your definition of electric displacement? So I will, I think, in order to explain a little more, I will again share the presentation. Just a minute. So just a minute. I think I'll just look at this. Okay. I hope you see the screen. And actually, it was a different one. Sorry. Okay, this is what I wanted to show you, the hysteresis loop. So the question, what is our definition of electric displacement, or dielectric displacement, as I would call it? So this is actually a measure of the charge density. So it's a charge relative to the area. So the unit for dielectric displacement that you see, the D that you see here, the unit for that is Coulomb per square meter. And the reason I say that it's almost equal to polarization is that if you look at the materials that we are working with, there's a very small difference between the two. But maybe just to elaborate a little more, the polarization is really the induced electric charges, like coming from the displacement here of dipoles. And if you add the basically the basic contribution even of a vacuum to that, then you will actually have D. So D will be the sum of the polarization, and then the electric field multiplied by the permittivity constant. So that's my definition of electric displacement. But in plain words, it's a measure of the magnitude of the charge density. Okay, I hope this answered the question. I will go back again, stop sharing, And then I can see there's a question more. Okay, actually it was thank you from Olivier. We have time if there should be other questions that appeared. While you may think, I think I will share the screen again just to show that we have the program of the webinars here. So this was the introduction today. I'm sorry if it was maybe a little bit ambitious in let's say the scope, because we had to cover a lot of different things today. The next webinar will also be done by me, and it's in 3 weeks. So it's about applications of piezoelectric materials. And I hope to see a lot of you again in 3 weeks. And I hope that you will find these webinars interesting, and especially compared to last year's. I think you'll find some really interesting new information by our two guest lecturers, Thomas Kelly and Tamas Savada. Okay, again, I'll stop sharing, and then I will say thank you for those who attended, and hopefully see you at one of the other webinars later. Thank you. Bye.